Okay, so I've chosen a few problems from the log applications, the 2 days of log applications that you have, just to kind of demonstrate here in a video for anyone's reference. All right, first question is a growth question. The other two are half-life questions. So the first question is dealing with money in an account. The question is, how long will it take for $9,200 to grow to $20,000 at an interest rate of 6.6% if compounded continuously? Okay, so we need to remember our continuous compounding formula, which is A equals PE to the RT. Which is essentially the same formula as the radioactive decay formula. The only difference is that the R we think of as negative in radioactive decay because, number one, it's a decay graph. It would be a decay. It would be going like this as opposed to like growing. So we think of kind of the R as being negative in the decay, radioactive decay. So this is a PERT, right? And so we need to kind of identify what is the information that we have. So how long is the question that we're being asked, right? So how long means we're going to be solving for t. Right? Will it take $9,200 to grow to $20,000? Right? And since this is a growth, we're starting this 9,200 is what we're starting with. Right? That's going to go in as our initial value. And our new value is going to be 20,000. Right? Because we're looking for how long does it take 92,000 to grow to 20,000? And then we still have our E. We have our interest rate of 6.6%, which we'll use as a decimal, 0.066. And we're solving for the variable t. Right? This is our unknown here. Okay, and once we get to the point where we have the formula, most of these problems, whether you're solving for t or whether you're solving for r, the rate, they all work the exact same way. Right? So we're going to, we need to isolate the exponential expression in order to isolate the actual exponent or the variable in order to be able to log both sides. So we're going to divide both sides, in this case by 9,200. And we're going to get e to the 0.066t is equal to it's approximately 2.1739. And then we'll take either think of it as taking the natural log of both sides, or rewriting this in this exponential as a log, right? So the natural log, if I rewrite the exponential as a natural log, the natural log of 2.1739 is equal to 0.066t, and then I just use my calculator to take the natural log of 2.1739 and then divide that by 0.066. And I get that t is approximately, looks like 11.8 years. So, 11.8 years, almost 12 years it'll take for that money to grow. All right, the next problem we have is a half-life problem. So this came from the second packet that you got, right? There was one day where you just got a double-sided sheet of paper. Those were all growth problems. The other packet had all half-life or decay problems. So we're given the half-life of thorium-229 is 7,340 years. Okay, it's irrelevant what the substance actually is. We really just care about the fact that it has a half-life of 7,340 years. And then again, it's asking us how long will it take for a sample of this to decay to 20% of its original amount. Okay, so this is an example of a problem that is in two steps, right? The first step is we have to use the info about the half-life to find the rate. Because we can't go directly to finding the how long, the time, without having a rate. So we're first going to use the information about the half-life to find a rate. Again, still using this time the radioactive decay formula. So the only difference between this formula and the one we used on the last problem is the negative sign in front of the rate to indicate that we're decaying. Okay, and because it's a half-life, all we really know is that the ratio, when we're talking about half-lives, the ratio of A to P is 1 to 2. If you're not comfortable with just going straight to 1/2 equals e to the negative RT, then you can really just substitute any two numbers in there, but it's really nice and easy to substitute 50 and 100. In here, right? Because again, if the 100 tells me how much I'm starting with, and if it's a half-life, then I'm going to reduce it by half. I'm going to go down to 50, and I'm going to do that in 7,340 years. So now I'm going to go ahead and solve this equation like I solved the last one. And I, again, solve it by either taking the natural log of both sides or just rewriting this exponential as a log. And then I'm going to take my calculator and calculate what the natural log of 0.5 is and divide that by negative 7,340. And I get, oh, it's not supposed to be t though, is it? It's supposed to be r. Sorry. Right? And I get a really tiny number. So my calculator set has an e to the negative 5 at the end of all those decimals. So this is actually 0.00009443 for my rate. And if we think about it for a second, it makes sense that my rate is really, really tiny. Because look at this. I have a half-life of 7,340 years. It takes a really, really, really long time for it to decay to half of its original amount. So it should make sense that the rate, it's a pretty slow rate, right? So that this rate is this tiny number here. So now that I've used the information I have to find the rate, step 2 is to use the rate to answer the question. Right? The question is how long, right? How long does it take? So I'm really looking for a t, right? A t value. Now that I have a rate, how long will it take for a sample of this to decay to 20% of its original amount? So again, let's go back and let's say I start with 100 grams or kilograms or whatever it might be of the substance. I have 100 e to the negative this tiny number, 0.0000943 to some time, right? That's what we're trying to find. If it's 20% of its original amount, and I started with 100, then hopefully it makes sense that I'm left with 20, right? 20 is 20% of 100. But the bottom line is once I divide through here, I'm going to be left with 0.2 over here, right? This is what represents that 20% of the original amount. So if you don't need to use an initial and a final amount when you have percentages there, you don't need to. You could just, stick in, 2/10 or 1/5 or 0.2 or whatever it is that you're most comfortable with. But if you need to, you could always kind of go back to using 100 as an initial amount. So 0.2 is equal to e to the negative really small number. And then again, we're going to natural log. And find that, let's see. It looks like it's going to be about 17,000 years, a little more than 17,000 years. Just want to make sure I plug that all in right. Yep, it looks like time is more than 17,044. or so years. That answer doesn't really sound familiar from my answer key, but I think it's right. So it was 17. It was definitely 17,000 something, but so it was a very big number. And again, it should make sense because the half-life is already so huge. So it should make sense that it takes 20% is more than another half-life away. So it should make sense that 17,000 is in the realm of your answer. Okay, one final example. This one is similar, but slightly different in that in the question that's being asked. So scientists have 15 grams of a new compound. Okay, so this is our initial amount. And it has a half-life of 16 hours, right? So this is going to be time in our first iteration. Approximately how much of the compound will they have in 24 hours? So we're given another time, right? So we're kind of given time twice here. The question is approximately how much. So the end, this is asking for, A, right? This is A. This is that ending amount. Okay? Still the procedure's the same. We still don't have a rate. So we still have to use the half-life to find a rate the same way we did before. Okay, so we could stick with the 15 grams that it's given us, which means that the half-life, half of it is 7.5, or you could just go straight to that 1/2 if you're comfortable with it. But 15e to the negative r times 16 is the half-life. 16 hours is the half-life. And we're going to go ahead and solve. 1/2 equals e to the negative 16r. Natural log of a half equals negative 16r. So the rate is approximately 0.0433. Right, so in this case, we're not going to go back and use the rate to find a time. We're going to go back and use the rate to find out how much. Okay, so use the rate to find how much remains after 24 hours. All right, so if we think about it for a second, if I write this formula down again, A of t equals A sub 0 e to the negative rt. Let's talk about what information we have, right? We have the initial amount, it's 15. We now have a rate because we calculated it. And we have a time because we're trying to figure out how much is left after 24 hours. So we have everything. The only thing we don't have is this. So this is actually an easier problem to solve because it doesn't involve calculating logs in the end, right? So A of t, or just A, is equal to 15 e to the negative 0.0433 times 24. And this I'm just going to plug right in my calculator. 15 e to the negative 0.0433 times 24. And it looks like it's approximately 5.3 grams. And again, if we think about it, right, it should make sense. The half-life of this is 16 hours. So after 16 hours, we have 7.5 grams left. 24 hours is half of another half-life away, right? 24 hours. So 32 hours would be a second half-life. So in 32 hours, we would have half of the 7.5, right, which is like 3.75. So it should make sense that we have somewhere between 3.75 and 7.5 grams left after 24 hours, right? So it's always, these questions should make sense. You should be able to look at your answer and say, in the context of the problem, is it logical, right? And this one is.